Hello and welcome to another Let's Study series. This is going to be on the book, on the topic of graphics programming. And I would sort of preface this that it is low-level graphics programming, or high efficiency, or modern graphics programming. Our entry into this topic is going to be this book that I've been reading for a couple years now. Not that I've gotten very far with it, but it is on the introduction to 3D game programming with the DirectX12 graphics API, written by Frank D. Luna. Okay, so I do have a digital copy of this book, so to save data on the video, we'll simply watch it on the screen capture instead. I found that per minute of recording, it is 94% more efficient memory space wise or storage space wise for the end result recording to screen capture rather than have a webcam capture my hand movements and the text movements and all that. So it saves a lot of space, which means I can keep more videos without having to buy more storage. It's a lot faster to upload, edit, and change and give to other people. So we'll just jump right into this topic. We will do some programming, hopefully, by the end of this video. I believe the first program is going to be just on some general mathematics involved with graphics. But the second video, or not sure how long the videos are going to be, it will be on drawing our first window and our first graphical object, which is simply just a triangle. But you have to start somewhere. So, Introduction to 3D Game Programming with DirectX12. So, just looking over this, we have our contents with a dedication, acknowledgement, and introduction. This introduction is going to cover the intended audience, the prerequisites most likely to do the code required in the book, the required development tools and hardware. So with graphics programming, it is a hardware-dependent sort of programming style, so you will have to have the hardware to leverage the programming that we will be doing. And then we'll be talking about using the DirectX SDK documentation as well as the SDK samples with clarity. And we have sample programs and online supplements, as well as a demo project set up in Visual Studio 2010. We'll be using Visual Studio Community Edition 2022 simply because that's the one I have installed on my computer at this moment, and it'll be very easy to work with, I believe. I've set up so many projects I can't even recall. I'll give myself like an 80% chance that I'll be able to set up the project without looking up absolutely anything. Okay, so we have a part 1 on mathematical prerequisites. This is going to be covering chapter 1 with what this is going to include. Chapter 1 on vector algebra, in which case we're going to be talking about vectors and their coordinate systems, left-handed versus right-handed coordinate systems, and then just some basic vector operations. And then we have some concepts such as vector lengths and unit vectors, or directional vectors. We have 2 operations, the dot product with orthogonalization, along with the cross product. We will have points, and then DirectX provides a bunch of mathematical objects, and one of these math objects is going to be the vectors. So we have DirectX math vectors, which we have various types, loading and storing methods, parameter passing, constant vectors, overloaded operators, miscellaneous set of functions, vector functions, and we get introduced to floating point error, which is important to know that computers are not infinitely precise and that we may become exposed to the errors that occur when we do mathematics with a limited computer. And so we have a summary and exercises for Chapter 1. So I believe we're going to get into the summary and exercises in this video for Chapter 1. But continuing on, we will have Chapter 2 of Part 1 moving on to matrix algebra. And so in the matrix algebra, we'll be talking about the definitions of a matrix. We have matrix multiplication, so the definition of a matrix, the vector matrix multiplication, so what a vector times or multiplied by, or just simply how it's affected by a matrix in its multiplication, as well as associativity of the matrix multiplication. So I believe what we're going to talk about is that matrix multiplication is not commutative. So we'll get to that, but effectively some mathematical properties that we normally think of when we have multiplication doesn't apply to matrices, such that A times B is not actually equal to B times A in the case of matrices. So it actually matters about how we order our matrix multiplication. We'll be continuing on and learning about the transpose of a matrix, the identity matrix, the determinant of a matrix with matrix minors and the definitions of those, as well as the adjoint of a matrix. I have no idea what that is. The inverse of a matrix, as well as DirectX math matrices. So DirectX, not only does it have math vectors, it also has math matrices. And so we're going to be introduced to various types and their functions, and we have the DirectX math matrix sample program, along with Chapter 2's summaries and exercises. We have Chapter 3 on transformations. And so on transformations, we're going to be talking about linear transformations with their matrix representation. And we'll be talking about, transformations are going to be talked about as sort of like a movement. So from left, right, up, down, right, and forward, back. So all 6 directions, as well as scaling and rotation. Matrices, and then we're going to be talking about affine, I'm not sure if I'm saying that right, affine transformations. We're talking about homogeneous coordinates, and I'm not quite sure what that means. I think homogeneous coordinates are going to be the coordinates that correspond both with what we're drawing as well as the screen coordinates. I'm not quite sure. And then we have the definition and matrix representation. We have translation, affine matrices for scaling and rotation, and the geometric interpretation of affine transformation matrix. So I don't remember any of this affine stuff. Affine. I'm not even sure if I'm saying it right. We'll just continue on with my best guess until I'm corrected. And then we have the composition of transformations, the chains of coordinate transformations with vectors, points, and matrices. We have associativity and change of coordinate matrices, and inverses and change of coordinate matrices. And we finish off with the transformation matrix versus change of coordinate matrix, as well as, of course, the DirectX transformation functions available to us from the DirectX library, along with some summary and exercises. So, after we finish that part 1 on vector algebra, we'll be continuing on. So that vector algebra is actually like linear algebra. So it's a topic I have never taken a class on, in which case the most amount of the vector or linear algebra that I've worked with is actually from this book, which is quite a bad thing. Not a good thing. I should have taken some kind of linear algebra in college. It was available. I don't believe I had any time in my schedule at any point in time to actually take it, but it would have been interesting if I had more time or money to be able to take that class and learn a little bit more about all these fun and very relevant and useful math functions and objects. So continuing on, we're going into part 2, on to the Direct 3D foundations. So we start that with chapter 4 on the Direct 3D initialization. And so we're going to be talking about the preliminaries about this information. So it'll be the DirectX12, so the DirectX 3D12 API overview We talked about the COM, objects, texture formats, swap chain and page flipping, depth buffering, resources and descriptors, multi-sampling theory, multi-sampling and Direct3D. As we're talking about feature levels, DirectX graphics infrastructure, the DXGI, and checking feature support and residency. We'll be talking about the CPU-GPU interaction. So what's interesting about graphics programming is that you are combining two processors effectively. So it's a multi-processor programming scheme of sorts. So we're both not only programming CPU code, we'll be programming GPU code, and we'll have to be syncing the resources and actions of these two processors. So we're going to be asking one to do one thing, and one thing to do another, one to wait on another, one to give information from one to another, store in a localized place, external place. It gets a little complicated, but it is something I like about graphics programming is that, well, it's a little bit more complicated. It's not a great thing that complexity is a good thing on its own, but multi-processor programming is quite interesting. Now, I don't even understand concurrency in C++ as well as I should, in which case I probably shouldn't even be going on and continuing on with this until I learned more about the concurrency methodology and terms and definitions and practices of working with concurrent programming with any language for that matter. I just need to know the concepts. So I understand like parallelization, I understand syncing or waiting, but I'm quite fuzzy on that. Okay, and then we're going to talk about the GPU-CPU interaction with the command queue and command lists, synchronization, resource transitions, as well as multi-threading with commands. Multi-threading with DirectX12 is one of its best hallmarks of being a good graphics API. Other APIs are like more single-threaded or less accessible to be split amongst several threads. I'm not quite sure what the terms and definitions would be around that, but simply DirectX12 does a better job at allowing you to extract the usefulness of it enables you to use multi-threading as a performance increaser with our programs more than other APIs. So with initializing Direct3D, we'll be creating a device, creating the fence and descriptor sizes. We'll be checking for MSAA quality support. We'll be creating our command queue and command lists. We will describe and then create the swap chain, and then we will create the descriptor heaps, and then we'll create the render target view, create the depth central view and depth buffer in view. We will be setting our viewport, and then finally we will be setting our scissor rectangles. So that's initializing the Direct3D environment with all of its resources. So Direct3D, DirectX12, or the DirectX API, it has a lot of build-up. So there's a huge amount of initialization. So your little hello world program where you just want to draw a single triangle, it's going to be huge and big. But the cool thing is that very, very much a lot of the code that you're going to write for this, even the most basic program, is going to copy over and come over to all of even the most complicated of programs. So once you do it once, if you understand how it works, and it does work, you never have to really touch it again, unless you want to do something very specific. And so in the most case, you do it once, you never have to do it again. You can even abstract it and hide it behind a function, and then you never have to even look at it again, which is some things that I've done in the past. Just hide the complexity. You don't need to see how it renders. You don't need to see how it initializes. You could just put it behind a function. And it does it once, and as long as what you're trying to program isn't requiring some complexity beyond your initial first programs, you just don't have to touch anything. So it's sort of an investment. So you initialize DirectX3D, you write your initialization code, and then you never have to write it again for the most part. So after that, we're initializing Direct3D. We'll be working with timing and animation. So, after I think the initializing 3D, all we're going to be doing is drawing a single triangle and nothing's happening. Okay? And so now we want to actually learn how to do animations where things change on screen. It's hard to have a video game where nothing changes on the screen. Even a click and... I don't even know. What's the most simple game I can think of? There's like a slideshow. Even a slideshow has animations and timing. And so we'll be talking about that. We have the performance timer, the game timer class, which I think is a provided timer class written by Frank Luna. And the time elapsed between frames and the total time. And then we'll have the demo application framework, which is sort of like, I think it's the best example of like a simple Direct3D game. Not really a game, but more of just a program. And I think that's what we're going to be shown here. Or the application framework is going to be talking about, well, the application in general. Because just looking down there, the message handler and whatnot. That's actually more of what I don't know. Is whether the 4.5 doesn't look... It sort of covers some things I actually don't quite know, I think. Or at least these are not looking familiar as much as they should. And we're going to finish off with a debugging 3D applications and a chapter summary. Chapter 5 is going to go into a little more specifics about the rendering pipeline. And so pipelines are a concept with architecture as well as with software engineering, where we are going to do simultaneous things or sequential things in order to get one final process. So we're going to do a piece of work here, a piece of work there, and then we're finally going to do a piece of work there to like show our results. And then with pipelining, we're going to have all 3 steps happening all at once. So instead of having one worker like cut a log, carve it into a boat, and then paint it, we're going to have 3 people. One cuts a log, one paints the boat, and then one finishes the boat. One cuts the log, one carves the boat, and then the other one paints the boat. And they all work in tandem, and it goes all the way down this pipeline. And it just works continuously. So we have some parallel processing because, well, we're going to have cores, we're going to have CPUs, we're going to have threads, we're going to have a whole bunch of stuff. A lot of complexity. But it's how we get high performance. So we talk about the 3D illusion, which is that all 3D graphics end up being a 2D texture in the end. So it's all sort of faked. We have the model representation, and we're going to be talking about basic computer color. So we have color operations, 128-bit color, 32-bit colors. Computers of the past didn't have a lot of memory space, as well as I think the monitors themselves probably couldn't present colors as depthly as we want them to. But we'll be working with those color systems. So we have the overview of the rendering pipeline, and we'll be talking about we're talking about the overview of the rendering pipeline. And we have we'll be talking about the input assembler stage, where we'll be talking about vertices, and then primitive topology. Topology is sort of, I'll leave that description to the book. I'm not too confident in my answer to that. But topology is basically how the data is organized in an efficient or convenient manner. So a point list is an array, like a one-dimensional array with various vertices in either 2 dimensions or 3 dimensions. We have a line strip, which is a bunch of lines connected one vertex to another. We have a line list, which is a list of line segments from 2 vertices. So every 2 vertices in this one-dimensional array is describing a segment. Then we have triangle strips, which are triangles based on, we have 1 vertex, 2 vertex. Well, we have the first vertex, second vertex, third vertex, which creates a triangle with those 3 vertices, and then the 4th vertex creates a new triangle based on the previous 2 vertices, and then it continues on from there. Every new vertex describes a triangle with the previous 2 vertices. And so that's how we can get some efficiency there, where the GPU can use that previously known information to continue on drawing quicker, more efficiently. Then we have triangle lists. Every 3 vertices describes a triangle in a dimensional array. And then we have primitives with adjacency. So some of the adjacency, I think, is in strips. And we have control point patch list. No idea what that is. And then we have indices, which is an interesting concept where we have our vertex data storing positions of vertices, and then we have indices that describe the connections between these vertices. And the indices can be of a lower type of data point. So it could be like integers. So it's an index. So if you have 3 vertices of floating point numbers, you can attach them together using integers to describe that the first 0, the second 1, and the third 2 vertices are all one triangle. So 0, 1, 2 describes that vertex 1, 2, and 3 are a triangle. And we can reuse that vertex information again. So say the second vertex is also a part of another triangle, or another one, or another. Instead of storing multiple copies of that vertex information, which is floating point numbers, which is vastly more costly than a short integer in byte space or bit space, we can simply re-reference it again using an index. So say we have a second triangle which reuses the second vertex, so one of the indices of that second triangle would be 1. So we don't have to copy over that vertex information, and we can use it several times, and it's just sort of a scheme of storing less data. And the less data you have, the less data you need to move, and the less data you need to reference and parse over. So less data means faster transfers and faster processing. So it's a good, indices are great. We'll move on to the vertex shader stage, which talks about the local space and world space, and then the view space. And then we finally have the projection and the homogeneous clip space, which is we'll be defining a frustum, which effectively anything outside the frustum gets snipped and cut and not drawn. And then we'll be talking about projecting vertices. We will talk about the normalized device coordinates and writing the projection equations with a matrix. So we'll be bringing in that matrix mathematics that we described in part 1. We'll be bringing that in, and then we talk about normalized depth value, as well as finally our first matrix, which is an important combined or compound matrix, which is the perspective FOV left-handed matrix. And after that vertex shader stage, where we talk about the tessellation stages, which I believe was just talked about briefly but not used, and I believe the geometry shader stage is talked about briefly and unused. And the clipping is this understanding how, if you're drawing outside of the space, how you end up clipping triangles such that you don't have to draw where the information is just going to be thrown out anyways. Because if you're drawing outside of a window, all of those pixels that you're drawing are just going to be tossed in the trash and not saved anywhere and not presented to the screen. And then finally, we're going to be talking about the rasterization stage using the viewport transform, backface culling, and the vertex attribute interpolation. Not quite sure what that is. But the final pieces is the pixel shader stage and the output merger stage. We have chapter 5 ending with some summary and exercises. And we have chapter 6 on drawing in Direct3D, in which case we're going to be covering in, I guess, more detail vertices and input layouts. vertex buffers. We have indices and index buffers. An example of a vertex shader with the input layout description and input signature linking. So not only do we have to describe, not only do we have to give inputs to the GPU to describe what's happening, not only do we have to provide the information to the GPU, we also have to provide what the description of that information to the GPU, which is interesting. It's an interesting concept. We have to both describe what we're doing and then provide that information in two different steps. Where otherwise you would just program, say, a structure or a class, and then you just call a constructor for that class. In the graphics programming, it's a little different. We have the example pixel shader, and when we have constant buffers, creating constant buffers, updating constant buffers, and then we have the upload buffer helper. I'm not sure if that's code provided by the book or it's simply functions provided by Direct3D. And we have constant buffer descriptors, and then we have the root signature and descriptor tables. And we're going to talk briefly on compiling shaders, in which case we can do offline compilation, where we compile shaders once and store the results for later. And then we have generated assembly. I'm not quite sure what that is. Maybe that's assembly code for the GPU. Who knows? I'm not actually too sure about that. But I guess I will be talking briefly about how to use Visual Studio to compile shaders offline. I'm sure we could figure out how to compile shaders offline using the D3D compiler in your System32 table. Or the D3D compiler library, or the DLL, the dynamic link library, to compile those shaders. I'm sure it should be easy. Should be. So we were talking about the rasterizer state, the pipeline state object, which describes our pipeline, and then we have the geometry helper structure. Don't have any idea what that is. And then we have the box demo, which is going to be our first true 3D program that we'll write. So we're going to have our first 3D shape on screen, and it'll be a manipulatable 3D shape. So we're going to spin the camera around a 3D cube. It looks like we're going to end with some summary and exercises in Chapter 6. So in Chapter 7, we're going to continue drawing in 3D, Direct3D, with a Part 2, where we're going to be talking about frame resources, render items, path constants, shape geometry. And with shape geometry, we're going to be talking about generating a cylindrical mesh. So cylinders, slide geometry, cap geometry, and then generating a sphere mesh or geosphere mesh. So in the end, everything is either a triangle or a quad, and then all of our basic shapes, your circle, your triangle, your sphere, your box, your prism, all of them are going to be made up of these triangles or quads. And so these are going to be talking about how to generate these primitives. Primitive shapes based on graphics primitives, because the graphics primitives are what we use. They are the atomics. The smallest value that we'll be working with is like a triangle or a vertex or an index of a vertex or color. In which case, we're going to be talking about, we're going to go into a shapes demo. The shapes demo in the book is a very simple scene in the book, which covers, not covers, but it has a three-dimensional scene, something like you would see in like a Unity, a very basic Unity or Unreal Engine sort of thing. Forget about textures, forget about complexity of the scene beyond this basic shapes. So we're going to have spheres, we're going to have columns, we're going to have boxes, we're going to have planes and surfaces. But it's very simple. But it's shapes. And once we get shapes going, it's going to be an interesting concept to go beyond that. And so with the shapes demo, we're going to be covering more about the vertex and index buffers, or for the first time. We'll be talking about render items, and then the frame resources and constant buffer views, and then drawing the scene. And then we have more on root signatures, in which case root signatures have their root parameters, they have their descriptor tables, the root descriptors, and the root concepts, or constants. And a more complicated root signature example, I think it's actually I can't recall what it is. Maybe we're passing a color in with our root signature before we draw. I'm not quite sure. I can't remember. But hopefully, I think it's actually like I'm not quite sure. But then we have root parameter versioning, and then we get into some of the more interesting stuff, which is the land and waves demo. Excuse me. The land and waves demo shows a simple scene of a randomly generated smooth hills and valleys landscape with a ocean scene where these ocean have ripples. So it's just like a 2D grid, but it is affected by random motion. And we're going to be rendering the land and the ocean together, which is a good one. But it's talking about generating a grid vertices and grid indices and applying a height function to that grid. And then we'll be talking about root CBVs, which are constant buffer views, as well as dynamic vertex buffers, which bam, 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 I really need to learn that. Dynamic vertex buffers. My vertex buffering with my old programs has always had this massive limiting factor, or not massive limiting factor, this massive bug where unintendedly, whenever you add something to the scene, and sometimes even if you remove something from the scene, the whole vertex buffer and resources involved have to be rewritten from scratch. So we get this huge stutter whenever I add something into a scene or remove something from the scene if I had did any buffer reduction sizes, which I normally actually try to skip, just so if you delete stuff, it doesn't cause any problems, but if you add more information, it does cause problems where the whole vertex buffer has to be rewritten. And it takes a split second. It gives a good stutter whenever you add something to the scene. But Chapter 7 ends with some summary and exercises. So with Chapter 8, lighting, we'll be talking about light and material interactions, and we're going to get started into material-based lighting methodology. But we have light and material interaction. I guess we're going to be talking about some little bit of physical properties of optics. And we will be talking about normal vectors and how to compute them and how transforming these normal vectors. We'll be talking about other important vectors in lighting. We'll be learning about Lambert's cosine law, and then we're going to be learning diffuse lighting, ambient lighting, and specular lighting. So how we have these different models of how light interacts with the world, or how light can be modeled, and then we're going to just combine them all in a certain ways. And so we're going to have various optical effects and optical properties of things in the real world, and we want to replicate them on the screen so that we have things that look realistic. Or what you can do is go in a completely different direction and start drawing things that are like alien or different. But generally, the human eye is, well, it's born with the capabilities. The human brain and eye combo is born with the capabilities of identifying information about a three-dimensional scene as it looks around its environment and has been trained all its life to understand like how shadows affect shape, size, distance, how light affects different things of different properties, shininess, smoothness, roughness, and then, well, we can take advantage of that training, take advantage of those skills that we have, and be able to provide more information about the scene than normal if we go a more realistic route. And so we're going to have a lighting model recap, a recap of the lighting model we'll be using. We're implementing materials along with lighting. So we have lights, so parallel lights, point lights with attenuation. We have spotlights, and then we have lighting implementation. So we have light structure, a common helper functions for lights, implementing directional lights, implementing point lights, and implementing spotlights, and accumulating multiple lights. And then I guess we're going to be talking about the main high-level shader language file, the HLSL file. And it looks like we're going to end off Chapter 8 with a lighting demo, talking about vertex format with a normal computation, updating the light direction, and update to the root signature, and completing those well with summary and exercises. In Chapter 9, we're going to be going into texturing. So we'll be talking about texture and resource recap. So I believe we're going to end up using textures before we get to this chapter. And we have been using resources before this chapter, but we're going to recap them. And we'll be talking about texture coordinates and various texture data sources with DDS overview, which I'm not quite sure what that is, creating DDS files. And then we'll be creating and enabling a texture, loading DDS files. And then we have the SRV heap, which I think is the shader resource view heap. And then we'll be creating the shader resource view descriptors, as well as binding textures to the pipeline that we'll be using at that moment. And then we have filters, describing magnification, minification, and anisotropic filtering. No idea what all those are. We have address modes. Don't know what that is. We have sampler objects. So this is already getting past like where I got as far as I could with the game. Well, not the game, but with this book, with this topic. So beyond here is well into the woods for me. I don't know what I am talking about, but we will learn that together, hopefully, as I progress through this book and make and program our demos. So we have address modes, sampler objects, where we'll be creating samplers and static samplers. We will be sampling textures in a shader, and then we will have the crate demo, which I believe is sort of that simple scene that we have with the various shapes, but now we have a crate in the center of the screen with a texture applied across that crate. So instead of being just a box, a green box, it's going to be a textured box. And so with that crate demo, we're going to be specifying texture coordinates. We'll be creating the texture and setting the texture, as well as updating the high-level shader language. And then we'll be talking about transforming textures, and then we have we had the lands and waves demo, and now I guess we're going to have the textured hills and waves demo. In which case, we're going to have textured land and water in this case. So the grid texture coordinate generation, texture tilling, texture animation. And then, of course, we're going to, not really, of course, some of the chapters don't have exercises and summaries, but Chapter 9 has its summary and exercises. Chapter 10 talks about blending, which I'm not quite sure what is, but I'm sure it's going to be useful for like bloom effects or merging two textures together, blending two textures or multiple textures together to get some interesting effect. And so we'll be talking about the blending equation, blend operations, blend factors, blend state, and with examples with no color right, adding and subtracting, multiplying, and transparency. So transparency is very important for me, I think, because I want to have some sprites in my programs, and I want transparency so I can have some very complex shapes without shapes. I could just have a very complex image with transparent objects, so we can have simple objects on screen, but we can, instead of being them static images walking around. We can actually have images overlapping each other, and it'll look very interesting, I think. We'll be talking about alpha channels, and then clipping pixels, and finally finishing off with fog, the thing in almost every video game, and of course summary and exercises of Chapter 10. Chapter 11 will be talking about stenciling. Stenciling, I know a little bit about it, but not enough to say any words. But we'll be talking about the depth and stencil formats and clearing with the stencil test. Describing the depth stencil state with depth settings and stencil settings, and creating and binding a depth stencil state, as well as implementing planar mirrors, mirror interview overview, defining the mirror depth stencil states, and drawing the scene with winding order and reflections. And we have implementing planar shadows. So I believe this is going to be the first introduction to shadows. So we have parallel light shadows, point light shadows, and general shadow matrix, and using the stencil buffer to prevent double blending, and shadow code. With Chapter 11 having some summary and exercises. We have Chapter 12 on the geometry shader, which of course, which we start with programming geometry shaders. And we have the tree billboards demo, which is actually, I just remembered, this is exactly what I want to do. Those trees are going to have some transparency in their textures. It's like a tree. It's a billboard. It's a flat square, but it's always facing the camera. But you can see around the tree. It's not just one square texture of a tree. It's actually a tree with various parts of that square billboard. You'd be able to see right past it, right through it, to see other trees and objects around the tree. Something like right next to the trunk or whatnot. But that's great. That's awesome. I need to learn this. That tree billboards demo is probably going to be the most relevant to the things I'm working on right now. Is the tree billboards demo. And so I'll be excited to get to that point, but that's 12 chapters ahead. About 8 chapters beyond what I've gotten to. And I'm thinking that most of the code that I've written in the past is not going to be particularly noteworthy of understanding. So I think I got things working, but I perhaps did not understand why they ended up working, or I just ended up not working. Those programs I've written, it just ended up not working. I have a couple examples of good programs that have succeeded, but I will say that I've certainly picked and chose my battles by adding or removing features liberally to get a result out rather than getting the result I wanted. So we'll get there eventually. So we will continue on with texture arrays, which we will have an overview of which, and we have describing us how to sample this texture array, as well as loading texture arrays and texture sub resources. And then we'll be talking about alpha 2 coverage, and with a summary and exercises of Chapter 12. Chapter 13 covers the compute shader, which I believe is sort of general processing of the GPU. We can generally program the GPU to do almost anything with the limited amount of operations that the GPU is capable of, as well as its limited precision. We can still ask it to do a great deal amount of parallel work that can even outrival the CPU processor we have on the computer. So depending on the workload, we could end up leveraging the capabilities and the processing power of our GPU and be able to get faster results than if we were programming it for the CPU. So compute shader is shaders, I believe, that are going to be used to do compute. They're going to compute something, and that could be, anything. such as image processing or mathematics, matrix mathematics, or some like physics engine stuff, a whole bunch of stuff, random number generation, texture generation, image processing. I already said that. A whole bunch of useful things. So we're going to start with the compute shader where we talk about threads and thread groups, and it looks like we'll be exposed to a simple compute shader with a compute PSO, which is a pipeline state object, and we'll have our data input and output resources with texture inputs and texture outputs, and then we'll have unordered access views or UAVs, and then we have indexing and sampling textures. We have the structured buffer resources, as well as copying CS results to system memory. We'll be talking about thread identification system values, appending and consuming buffers. We'll have shared memory and synchronization. And then we'll have the blur demo, which I've never seen before, which is interesting. We're blurring theory. Not quite sure what that is. I'm sure it's going to be like Gaussian blurs, how we merge two textures or noises together. We have render to texture, which is interesting. So I guess we're going to be rendering maybe perhaps a random blurry texture to a texture that we can use elsewhere. We have the blur implementation overview, and then the compute shader program. We have further resources available, so probably referencing us to go read something else beyond the book, which is important to note that this book may not talk about compute shaders as much as we want, but thankfully it looks to be that we will have further resources for us to continue our education in that regard. So it will perhaps point us in the direction of more resources in the future. We have the chapter 14 on the tessellation stages. We have tessellation covering primitive types. We have tessellation in the vertex shader. We have the hull shader with the constant hull shader, a control point hull shader, a tessellation stage, with the quad patch tessellation examples, with the triangle patch tessellation examples, and the domain shader. We talk about tessellating a quad, so triangulating it, or turning a quad into triangles, or turning a quad into many quads. And we have the cubic Bezier quad patches. We have Bezier curves, cubic Bezier surfaces, and cubic Bezier surface evaluation code, and defining the patch geometry with summary and exercises, finishing that. So that covers part 2 of drawing in 3D, Direct 3D. In part 3, we'll be covering additional topics in more detail, which I believe it's talking about building chapter 15 starts with building a first-person camera, as well as dynamic indexing. So we have the view transform review, the camera class, which the camera class provided by the book is very useful. I've rewritten it myself and not a single bit of an improvement done that way. But we have the selected method implementations, XM vector return variations, set lens, I remember using that, derived frustum information, transforming the camera, building the view matrix. I've done those things before with varying degrees of success, mostly not successful, but I got it to work in a couple of examples, but it gets a little complicated in how you get it set up. Usually I end up messing something up, and then sort of the world warps around. It doesn't maintain its consistency of a realistic environment. Gets close, but things start warping around whenever moving the camera or rotating the camera along. And we have the camera demo comments talked about in its own section, and then we get to talk about dynamic indexing, which I'm not quite sure what that is, but it's in there. with Chapter 15 having its summary and exercises. We have Chapter 16 on instancing and frustum calling. So instancing is a interesting concept to myself. I would say that I have never gotten it to work properly or at all. But I understand its incredible efficiency gains by instancing. Instancing is effectively you store the information to draw a single object, and then you replicate that information not on memory, but you reuse the information about drawing one object to draw it several times in various manners. So you can have one tree be a tree, and then all of the resources are reused to draw another tree with just some slight variations. A little taller, a little more rotated, a little around, but you reuse all of that information. And most of the information required to draw that tree, you just simply reuse it, and it's already stored in memory, so it's very highly efficient to instance what you're drawing. So instead of having various trees all with their own vertex information and textures, you can have one tree with various parameters and then draw them several times. Draw as many trees as you have different parameters around the scene, and you can save a lot of resources. And instancing just looked like this amazing technique that I never got the grasp of. But I understood it at least as best as I could in the past, and we need to learn a little more about that. And so with Chapter 6, it starts with hardware instancing, which is drawing instance data, with instance data being described in the next section, and creating the instance buffer. And then we have bounding volumes and frustrums. And this is important. We get to talk about the DirectX math collision library. So the math collision header or library, whatever you want to call it, or whatever it is, I should say, provides us functionality for detecting collisions, which is a very important concept in video games, and as well as doing any sort of physical modeling. We need to know when objects touch each other, or when they're inside of each other, or contacting each other, or not contacting each other. So collisions or overlapping is an important concept to be able to calculate. In which case we'll be talking about boxes, and rotations and axis-aligned bounding boxes. And then we'll be talking about spheres, and then frustrums, which are sort of rectangular areas. And so with these frustrums, we can define a collision detection system using these frustrums, and we can detect what objects are in our scene or not. And so we can skip even beginning to draw a complex object that happens to be behind the camera. If that object is behind the camera, there's no reason for us to draw it. It won't ever end up changing this image in front of the camera. The image generated of what would be the view of the camera. And so we can do frustum calling, where we skip drawing things behind us instead of simply throwing away all of those pixels that we'll be generating. And so that is another major optimization, and is I would say most definitely required of high-level games or just high-cost applications. We have to be able to write our code in an efficient manner. And one of those is frustum calling. And so we'll be constructing the frustum planes, and we have frustum and sphere intersections, and then frustum and AABB intersection, which is the axis-aligned bounding boxes intersection. And then we'll be finishing Chapter 16 with frustum calling, with some summary and exercises. So a pattern that I'm looking here is that I got through the first section of the book a little bit, not quite well, and then it looks like I continued on my own into other sections, skipping over other information, which I think probably ended up having very vital background information about sort of the functionality and data types and concepts that these later sections or these later topics required. And so I probably shot myself in the foot by jumping too far ahead with how I approached this book. So I got through the first section, took me a very long time to do that. And then looks like I jumped ahead into various things, and I just attempted to learn them and attempted to apply them right into my programs as they are, rather than start to finish with the book. That's what I'm getting the vibe or the feel of how I approached the book. And my mistake, most likely my mistake with how I progressed myself through this book. And we have chapter 7 on picking, which I actually don't know anything about. But we have sections on screen to projection window transform. We have world, local space, picking ray. We have ray mesh intersection. We have ray ABB intersection, ray sphere intersection, and ray triangle intersection and demo application. So I wonder if picking is going to be selecting. So if we're shooting a ray through the camera, or we click on the screen, we want to be able to pick an object. That's my idea. I may be completely wrong, but that's what I'm thinking picking is. Not described as just by the section titles. With chapter 18 covering cube mapping, which I believe is going to be like our skyboxes and stuff. So cube mapping, we have our environment maps, so loading and using cube maps in Direct3D. We texting our sky. Okay, so that sounds like a skybox. We'll be modeling reflections, so most of the reflections in the scenes that we'll be working with, or any scenes that you'll be working with or being used in video games, are not reflecting off of everything in the environment. Most of all, they're just reflecting off of the skybox available. So that puddle doesn't care about what's above it being an object, but it does care about the clouds and the sky. In which case, it gets a lot done just by showing that. A puddle with the clouds in it looks interesting. Especially the more interesting the clouds are, the more interesting the reflections are. But I will assume that reflections are very costly, expensive. Okay. And so we're modeling reflections. I think we're going to be talking about those. And that will probably describe us the cost involved with reflections. I apologize, I'm very tired. And we have the dynamic cube maps, the dynamic cube map helper class, and the building of the cube map resource with extra descriptor heap space, building the descriptors, building the depth buffer, as well as the cube map viewport and scissor rectangle, as well as setting up the cube map camera and drawing into the cube map. Dynamic cube maps with the geometry shader and summary and exercises. So for chapter 19, we'll be talking about normal mapping. I think we're going to be talking about the motivations behind normals and normal maps. We'll have texture and tangent space with a vertex tangent space and transforming between tangent space and object space. And then normal mapping shader code with some summary of exercises. And chapter 20 is covering shadow mapping, in which case we'll be rendering scene depth, orthographic projections. We have projective texture coordinates and code implementation of which, and with points outside the frustum and orthographic projections. We have shadow mapping. Okay, chapter and section title being the same. We have algorithm description, biasing and aliasing. We have PCF filtering and building the shadow map. We have the shadow factor and the shadow map test. And finally, we have rendering the shadow map. Then we have large PCF kernels. Don't know what those are. We have DDX and DDY functions. And solution to the large PCF kernel problem, and an alternative solution to the large PCF kernel problem. It's very interesting. I was reading the AMD 64 architecture documents, and DDX, DDY, that sounds similar. I know it's all acronyms, and probably acronyms overlap a lot easier than we would imagine. But that sounds like some architecture, like low level stuff. I mean, it's kernels. Of course it would be low level. We have chapter 21 covering ambient occlusion. We have ambient occlusion via ray casting, and there is screen space ambient occlusion with rendering normals and depth pass. We have ambient occlusion pass with a reconstruct view space position, generate random samples, and generate the potential occluding points. Perform the occlusion test, finishing the calculation about implementation, and a blur pass using the ambient occlusion map. I don't know what ambient occlusion is. I think ambient occlusion is like the shadows with like geometry. So a corner is darker than an edge of a box, effectively. Like a room is darker than an open room. Stuff like that. Chapter 22 covers quaternions. Ooh, very complex stuff, but incredibly useful mathematical concepts. And we will be talking with overview of complex numbers, with definitions and geometric interpretation of them, along with polar representation and rotations. And then we have quaternion algebra, which is very complex linear algebra. And we'll be talking about the definition and basic operations of the quaternions. We have special products of quaternions, their properties, their conversions, and how they conjugate and norm. And we have inverses of quaternions, and then we have a polar representation of quaternions. We have unit quaternions and rotations. We have the rotation operator. We have quaternion rotation operator to matrix, and matrix to quaternion rotation operator, as well as composition, as well as quaternion interpolation. Quaternions are used to rotate three-dimensional objects as well. It can describe rotations as well as other operations. They're very complex data structures, but they're incredibly useful. I believe I got quaternions to work with my physics demo of it's a landing on the moon simulator. It's a very basic three-dimensional scene with a two-dimensional sort of texture of a cockpit, but it is a three-dimensional scene being rendered with some real physics, with some forward Euler mathematics. So it's a real physics scene, and effectively you have a flat plane, you have a lander that you begin the scenario with a downward trajectory towards the lunar surface, or I think you just start above the lunar surface and just quickly fall down. And you have to angle the you have to angle the moon lander, as well as firing rockets. The main thruster, which points in the up direction, and you have to cancel out your velocity such that you land not only softly, canceling out your acceleration due to the moon's gravity, but you cancel that out using the thrusters and the available fuel reserve that you have to land softly. So effectively simulating landing on the moon. Now, was it an incredible game and super fun? Not at all. But it did show me some interesting concepts that, due to the lack of geographical features on the moon, without seeing the shadow of the spacecraft, knowing the sizes of not knowing the sizes of craters and rocks, your stereoscopic vision perhaps is a little better, but the stereoscopic vision, or just the analysis of an image and judging how far away you are from the ground or your altitude, is very difficult. The lunar surface, even the very basic one I textured, is very difficult to understand. Like, how far away are you? Because those craters could be the size of a house or the size of a swimming pool. You don't know. Every crater sort of looks the same. You don't know how big the craters are. Without knowing how big the craters are, you don't understand the features of the surface. Without understanding the features of the surface, you don't know how far away you are from them. Without using, say, radar to give you a good altitude measurement. And so it's an interesting thing that even with my very, very simple graphical demo, it showed the concern probably facing the lunar landers of today and the past, that optically it is very difficult to tell altitude just out looking out your window. It's incredibly difficult. There's no landscape features. There's no houses. There's no roads. There's no power lines. There's no trees. There's no hills and rivers and creeks. Nothing. So without all of these well-known objects baked into our memory, it's very difficult to understand how high up you are. So from the surface, you could be very high up and burning your fuel too early, running it out, and then collapsing on the surface too fast later without fuel to slow you down, or you could be burning way too late, thinking that you're a lot higher than you actually are, and then crashing into the surface. And so the very basic program was able to express this concern, and it'll be interesting to learn about the historical ideas about how they dealt with that. Now, I believe they dealt with that using both having human eyes, which use two eyes, which give you stereoscopic vision, so three-dimensional, you have depth perception, effectively, which is an important thing that is missing from my program. My program is rendering only a 2D image of a 3D scene, so there is no of that. So perhaps the problem isn't as bad as I think it is. As well as having radar. As well as landing in such a way that they can see their shadow as they approach the surface. Because the shadow is an amazing reference point of like how high up you are. You can sort of do that triangulation math in your head just very, very naturally. And have that spacecraft... just be able to analyze the environment. When you can see shadows, you can understand height and shape and size a lot quicker than without. And that's quaternions. We were talking about quaternions, or what's the last thing we were talking about? Chapter 22, and we're reviewing the complex numbers, quaternion algebra, unit quaternions, and quaternion interpolation. And we have DirectX math quaternion functions. So DirectX is going to provide us some quaternion functions. And we have a rotation demo. Chapter 23 is going to be our last chapter. And it's going to cover animation. In this case, we're going to have a character animation. I believe it's like some barbarian character. But it's a humanoid character animated. We talk about frame hierarchies, mathematical formulation of them, where we talk about skinned meshes. So we're going to texture this mesh. We have the definitions of a skinned mesh, and then reformulating the bones to root transformation, as well as talking about an offset transform, and animating the skeleton, and calculating the final transform, and where we talk about vertex blending, and loading animation data from file, which, of course, to do this sort of file processing, we need a header, we need materials, subsets. We have the vertex data and the triangles. We have bone offsets and transformations. We have a hierarchy of this information, or hierarchy of bones. And then we have animation data and M3D loader. Not sure what that is. Perhaps it's a resource provided by the book. And then finally we have that character animation demo, which is sort of tying, I think, everything together at the end of the book, where you have a skybox, you have textured resources in the scene. So you have like a textured surface, you have textured cylinders, spheres, boxes, you have reflective spheres, you have reflective surfaces, Then we have this character in the scene with animation and bones, so it's able to walk around. We have shadows, and we have, everything comes together, and we have what looks like a game. It looks like a game. It's not the most beautiful game. It's not the most complex game. It certainly doesn't have any gameplay loop or features, but it's a game. It's the graphical representation of an early game. And I think it's great. I'm not quite sure how to start with it or that, but I've seen it and it looks interesting. And so we're going to get to that point. But what's most interesting is the concepts behind how we get to there. Not how you just open a model, load a model in, click some shader options in a graphic engine, and then, everything's done for you and it's all available. This book is going to be talking about how we get there, how the things work in the background, how they actually function. And so I find that interesting more than anything. And we have of course, we will finish with an appendix. Any complicated book is going to have some good appendices. We'll be talking about Introduction to Windows Programming. So I have a other Let's Study series on programming Windows, 5th edition, in which case we'll be talking about the Win32 program, Win32 API of the Windows operating system. And so with that, so DirectX is a Windows operating system graphics programming interface, or graphics application programming interface. So it works on Windows, and I think only Windows. And of course, then, to draw our scenes, we're going to need an application. We're going to need a window. We're going to need to interact with the operating system, as well as grab input and output from the operating system, which is already gathering keyboard and mouse commands and clicks and drags and all this information. So we're going to get an overview of that with various resources. We'll be talking quickly about events. So Windows is an event. Windows operating system is an event-based or event-driven system. We'll be talking about the message queue, how messages and message loops work. We'll be talking about the GUI or the graphics user interface. We'll be talking about Unicode. Looks like we're going to get a basic Windows application and explaining the basic Windows application with the includes that we need to use, the global variables we'll have, prototypes, the win main versus a normal main function, the win class and registering that win class, and then creating and then displaying a window, and we have the message loop, the Windows procedure, as well as the message box function. And then we'll be talking about a better message loop, which is an interesting topic to recover from or look at. I need to cover that for sure. That finishes Appendix B, which that whole Appendix B, I will read that. But it's interesting to note that I'm reading a more definitive and much more verbose, not more verbose, but much more informing book on the topic rather than just an appendix. So I would love to see if there's any glaring conflicts or mistakes or anything between the two resources. Most very likely that they're going to be incredibly overlapping and no mistakes are going to be found. But it'll be interesting about what applies from one book to this book to the modern graphics application programming. Appendix B, covering high-level shader language reference. So we'll be talking about the variable types that we have available to us in the high-level shader language, with scalar, vector, matrix types, with arrays, structures, and then what type definitions we have available to us, or how we can define our own data types. What are swizzles? I just read that. I just looked at it. I don't know what that is. But we have variable prefixes, castings, so casting from one type to another. We have keywords and operators, so what keywords we have in the high-level shader language, and then what operators we have to use. And then, of course, like how programs flow through these through these files or through these programs we write. And then we cover some functions with user-defined functions that we can do and built-in functions we have, and then constant buffer packing, which I don't understand. We have Appendix C on some analytic geometry. So once again, another class I've never taken before, analytical geometry. But is covering rays, lines, and segments, parallelograms, triangles, and planes. So these various three-dimensional concepts. And we'll be with planes. We're going to be talking. It looks a lot about planes with DirectX math planes. We have point, plane, spatial relation, construction of a plane, normalization of a plane, transforming a plane, the nearest point on a plane to a given point, and array plane intersection, as well as reflecting vectors and reflecting points, as well as a reflecting matrix. And we finish off with this is interesting, exercises in the appendix. And we have Appendix D, which is solutions to selected exercises. This is interesting. I didn't know there was any solutions in the back of the book. Okay. And Appendix E has a bibliography full of references and the bibliography of the book and further reading, which is great. And then followed by the index. As any good book would have an index, I think books are they required to have an index. I don't think any self-respecting publisher would publish a book without an index. I think I have seen a book without an index. Okay, well, I've been talking for a while. I need to give my voice box a little break before it tears itself apart, as well as I lose my mind. And it looks like the only thing that we got through is the preface. I'll read the acknowledgments before I head out, but from Frank D. Luna, the acknowledgments is, I would like to thank Rod Lopez, Jim Letterman, Hanli Luan, Frank Falk, Tabon Wu, Tomas Sandros, Eric Sandeglin, Jay Tennant, and William Goshnick for reviewing earlier editions for the book. I want to thank Tyler Jinkard for building some of the 3D models and textures used in some of the demo programs available on the book's website. Okay, this is some information, so the programs are available on the book's website. Also want to thank Dale E. LaForce, Adam Holt, Gary Simmons, James Lambers, and William Chin for their assistance in the past. In addition, I want to thank Matt Sandy for getting me the DirectX12 beta and the rest of the DirectX team that helped answer questions for beta users. Finally, I want to thank the staff at Mercury Learning and Information, and particularly David Paglia, the publisher, and Jennifer Blaney, who guided the book through production. Okay, so that gets us through the preface of the DirectX introduction to. That finishes the introduction or the preface to the introduction to 3D gaming programming with DirectX 12 by Frank D. Luna. Thank you for watching or sitting through this video. I hope you found it at least a little bit helpful in some regard. At the very least, it's very interesting. I love to be able to say this. I want to put this on like a little quote for me to finish off every single video. This video has already accomplished its goal by the very creation of it. The creation of this video was was the very motivation to read the book. And so by creating the video, it has forced me to read the book. At least this is a small part of it, but it has gotten me from, instead of sitting on the couch or doing nothing or playing video games or short-term dopamine rushes, I'm actually getting some measurable amount of work done. So just because this video has been created at all, it has accomplished its goal. But I'm not quite sure how useful it is for anyone else. Perhaps it is simply a waste of space in YouTube servers or whatever data, any location that this video is put or read. Perhaps it is negatively helpful that this video exists. Who knows? But I hope someone out there can have some enjoyment with this video or some learning perspective. At the very least, this video is describing and showing a real-life person of how they're dealing with this topic and how they're learning it. And so at least it is a representation, or at least a truer representation of someone's learning process of this book. Someone being just me. So a sample size of 1. Who knows how useful that is? Not quite sure. So instead of talking about this and talking about it more, good night. Thank you for watching. I will be continuing on with more videos on perhaps various more topics in the future.